Okay, so today we're going to finish topic 1, atoms in the periodic table, with the final lesson 5, acids and bases, which is found on pages 48 to 54 in your textbook. So as usual, we're going to start with our connected. So here we have acid in action, figure 1. The soft tissues of this bog body have been preserved by acidic conditions in a wetland. Circle the part of the bog you think is most acidic and write a sentence to justify your response. So here is our area, and the area circled should appear wet and contain dead plant matter. Because plant matter is decomposing in this area, more acid is formed. Why do bog acids react differently with the bones of the bodies than they do with the organs, hair, and skin? So the acids must preserve the substances of the organs, hair, and skin, and wear away the substances of the bone. Then lastly, how are pickles similar to bog bodies? So both are preserved by acids. Acids. An acid is a compound that reacts with metals and carbonates. It tastes sour and turns blue litmus paper red. Almost all acids contain the element hydrogen as a positively charged ion of a single hydrogen atom. As the dead plant material decomposes, acids form, which we learned about our bog body. That's what that's referring to. So our reading check here. What other things can you think of that might be preserved? And we can include things like mummies, fossils and rocks. All of these are things that can be preserved, like our bog body. Properties of acids. Acids are an important part of our lives. Folic acid, found in green leafy vegetables, is important for human cell growth. Hydrochloric acid in your stomach helps with digestion. Phosphoric acid is an ingredient in plant fertilizers. Sulfuric acid drives many types of batteries, giving it the nickname battery acid. Reactions with metals. Acids react with certain metals to produce hydrogen gas. Acids are described as corrosive, meaning they wear away other materials. A few metals, such as plutonium and gold, do not generally react with acids, but most other metals do. Reactions with carbonates. Carbonate ions contain carbon and oxygen, atoms bonded together with an overall negative charge, so CO3 minus 2. Geologists use this property of acids to identify rocks. For example, if acid poured on a rock surface produces carbon dioxide gas, then the rock may be made of limestone. Gold is another test. So the gold object being tested is scraped on the touchstone. Then acid is poured onto the streak. Why do you think that the more gas bubbles the streak produces, the lower the purity of the gold? And that's because gold does not react with acid, like we just said. Other metals are present in a lower purity gold, and they cause the reaction. Sour taste. Citrus fruits, such as lemons, grapefruit, and oranges, all contain citric acid. Although sour taste is characteristic of many acids, it is not one you should use to identify a compound as an acid. It is not safe to taste unknown chemicals. Reactions with indicators. Chemists use indicators to test for acids. Litmus paper is an example of an indicator, or a compound that changes color when it comes into contact with an acid. Acids turn blue litmus paper red. Litmus is a natural indicator. So here we have figure 3, oysters and acids. What effect do you think an increase of acidity of ocean water has on oyster shells? And the acid reacts with the carbonate ions in the shells, dissolving them and causing them to grow more slowly. We also have figure 4, hydrangeas and acidity. Some hydrangeas produce blue blossoms when they grow in acidic soil. What might you need to do to the soil if you prefer pink flowers? And you might need to make the soil less acidic. Reading check. The text above says that many acids taste sour, but also states that oranges and tomatoes contain acid. suggest at least one reason why these fruits don't taste sour. Oranges don't contain enough natural sugar to overcome the sour taste of citric acid. Properties of bases. A base tastes bitter, feels slippery, and turns red litmus paper blue. The properties of bases are often described as the opposite of the properties of acids. In chemical reactions, acids are more likely to give up a positively charged hydrogen ion, which is really just a proton. Bases are more likely to accept a proton. Bitter taste. Have you ever tasted tonic water? The base known as quinine causes a slightly bitter taste. Other foods that contain bases include almonds and cocoa beans. Slippery feel. The slippery feeling of your shampoo is a property of the bases it contains. Just as you should avoid tasting an unknown substance, you should not touch one either. Strong bases can irritate your skin. A safer way to identify bases is by testing their properties with a litmus test. Reading check. How are acids and bases similar? Why are they said to have opposite properties? So although acids and bases are both compounds, they have different tastes and textures, and they have opposite effects on indicators. All right, so now for the planet. Acid or base. Imagine that you need to determine whether each liquid pictured is an acid or a base. Plan an investigation to determine whether each liquid is an acid or a base. List any materials you will need and predict your results. So solutions could be tested with litmus paper. The acids will turn blue litmus paper red. Bases will turn a red piece blue. Predicted acids are the orange and the vinegar, and predicted bases are the shampoo and the glass cleaner. Neutralization of acids and bases. If you mixed an acid and a base together and then tested the final result, you would find that the process produced a neutral solution of a salt and water, which is neither acidic nor basic. The reaction between an acid and a base is called a neutralization reaction. The results of a neutralization reaction are not always neutral. The final results depend on the volumes, concentrations, and strengths of the reaction. So here we have hydrochloric acid with sodium hydroxide, which creates sodium chloride and water. Reading check. Why are the result of a neutralization reaction not always neutral? And the volumes, concentrations, and strengths of the reactants determine the neutrality of the result. Common salts, figure 5. Each of these salts is the result of a neutralization reaction. We need to complete the table with the formulas for the salts produced. So we have potassium iodide, sodium fluoride, sodium chloride, which we need to write. We get the sodium from sodium hydroxide, and we get the chloride or the chlorine, which makes the chloride, from hydrochloric acid, making NaCl. Lithium bromide, we have lithium, we have bromine. Potassium nitrate, we already have written, and calcium chloride, we have CaCl. So sodium fluoride is one of several fluoride compounds used in toothpaste to help prevent cavities. Just a fun little fact there. And that brings us to our lesson 5 check. So first, draw a line to match each formula with the type of compound it represents. KOH is a base, NH4Cl is a salt, and HNO3 is an acid. Why is vinegar stored in a plastic or glass container rather than a metal one? Vinegar is acidic and it would react with the metal in the container. What are the products of a neutralization reaction between hydrochloric acid and magnesium hydroxide? We would have water, or H2O, and magnesium chloride, MgCl2. Many stone buildings are made from limestone, which is primarily calcium carbonate. What happens to such buildings over time if they are exposed to acid rain? So the acid reacts with the carbonate and the buildings are damaged. You are given an unknown solution and asked to determine whether it is an acid or a base. What properties of acids and bases could you use to classify the solution? What properties would you use to make this determination? So I could use its reaction with carbonates or metals or its effect on indicators. I would not taste or touch this solution. And that concludes Lesson 5.